All right, so again, we're going to try and determine the coefficient of kinetic friction. And do so by starting with this apparatus, and your job was to determine what the free body diagram would look like if I was trying to pull this at constant velocity. Now that should take you about, I don't know, 4 seconds. So let me see. So I just saw the chat. Yes, my screen was black. I didn't even notice. So yeah, how weird it's getting now. So let's start with the forces that are on here. Kaylee, give me a force.
Friction
How would I draw that?
to the left.
Okay, so we're going to assume that the box is sliding this way. So friction must be to the left. Excellent. Fatima, give me another force, please.
Weight pulling down.
Weight pulling down. That's right. I'm going to draw the weight. And I'm pretty sure the weight's probably going to be more than the frictional force. I have a hunch, but we'll see. Carolina, give me another one.
Normal force going up.
I would have to draw a normal force upwards. Now, I'm going to be careful here because I think you would agree that the normal force should be the same size as the weight. Right? We're not drawing this in a way that is inconsistent. We want to be consistent. Well, our expectation here is that the normal force and the weight are balanced. In fact, we had tried to set the track up in such a way that it's level. And I'll talk about doing that here in just a minute too. But yeah, we believe those are going to be balanced. And let's see, Nevaeh, give me another force, please.
Gravity.
We already got gravity here, so that's the weight.
Is it static force?
Well, we're looking for kinetic friction. We're going to assume that it's already sliding. So if these were the 3 forces that were acting, I'm pretty sure that it would just be slowing down because it looks unbalanced. But our goal is for us to be moving it at a constant velocity. So what direction would I have to draw an arrow for that to balance out so it can move at constant velocity? Spencer, what do you got?
Is it the tension in the string going to the right?
Sure, I'm going to pull on it with a string, so we'd have tension to the right. Now, I hope you guys are all thinking the same thing I am, and I'm not so sure of that after that exchange, but we want balance here. Which law are we working from? First law or second law? First, we would like the car to move at a constant velocity. The car can't stay still. We want kinetic friction. And kinetic friction requires that it be moving, but it doesn't have to be accelerating. So we would like balance. Now, the reason for this, and I hope you guys can follow this, is that we can break this up into the X direction and the Y direction. Assuming it's the first law, our hope here is that we have the means to figure out the frictional force and the normal force. Right? If it's balanced, and we make extra care to ensure that it is balanced, then we could measure the tension in the string. That would be equivalent to the frictional force. And we can measure the normal force if we know the mass of the cars. So we're actually not measuring friction or normal force. We are determining them indirectly. What we are measuring is the tension force and the weight. And we believe that that's going to be equivalent. So the first part about a lab is starting with some fundamental concept and then determining things that you could measure that could get to the fundamental concept. So you can't start a lab with the idea that you're just going to measure the frictional force. In fact, the graders know that. They want to know what you're going to measure that could be used as the frictional force. Similarly, for the normal force, you can't measure the normal force, but you can measure other forces that can tell you what the normal force is. Make sense so far? All right, so let's talk about our experimental design choices we're going to make. And I've got a force probe. It is right here. Now, force probe is like a spring scale, but the downside of the force probe is that it reads something like right now. You see that, don't you, on the screen? And what's this? Almost half a Newton. Now, the real issue here is that a force probe like this just measures something else, doesn't actually measure force. But right now, there's nothing connected to it, but it's still registering that it's registering a force. It should be 0. The problem is that all probes require a certain amount of calibration. And for probes that don't auto-calibrate, you have to start knowing that this is now 0. Whatever we measure on top of this, you will have to select this number and subtract it from whatever we measure. That's calibrating your probe. It's not a bad idea if you're using any kind of probeware to throw in an extra sentence that says, spend a minute to calibrate your probe. It makes sure your test graders understand that you are considerate of the things that contribute to your data. Now, we want the track to be as level as possible. So you need to indicate a way to make the track level. I've provided something this time. I don't usually break all these out because they just get damaged too quickly, but you'll see a little protractor here on the side of the track. It's not anything particularly exciting, just a little ball on a string with the protractor measurements on it. And it's also got on the back something that allows it to make sure it's aligned with the track. So that when we set it on here, we can be reasonably sure when the ball settles down that whatever it points to is the angle of the track. So let's see, the angle of the track. Almost 0. It's going to be close enough because I'm not going to change it. So let's say 0. So the track is balanced, even if it's all warped because it's on a, my GoPro here. So balanced track, cart, and I'm using a friction block on the bottom of the cart. Now, here's the thing. If this were a real lab, you would have to indicate how you're going to measure the mass of the cars. You have to tell them what you're going to do. I'm confident that you guys know you're going to use a scale for the cars. We're just going to use the fixed number that I happen to know because I measured it earlier today. It's 150 for the block and 500 for the car. But don't always assume. Make sure that you put in there as an experimental design, anything that can be measured, you should describe how you're going to measure it. So I've got a string already tied to the car. Unfortunately, the string is too long, but I'm going to use it anyways because there's another lab we're going to do later on that needs a longer string. So I've got the cart way over there, and I've got my force probe, and the force probe does provide a live reading. So all I'm going to do is I'm going to pull the cart across the track, and I'm not close enough, and I can't do it all at the same time. So John, you're in charge of telling us what this number is, okay?
All right.
It will bounce around some, and it's delayed. All right. What would you say was a good number for that?
It was 4 point. I saw it at 3.5 toward the end.
Okay.
I always say that.
3.5 towards the end. So that's not the actual tension force, right? Because right now, this is what the calibrating value is. You have to subtract this from the 3.5 that John says was on the meter. So you now know the frictional force. We also know a way of getting the normal force. The cart was 500 grams and the block is 150 grams. So we have 650 grams of mass over there. So you can get the normal force from that. When calculating normal force, you should use a reasonable number for G, not 10. 9.8 would be most appropriate. So let's see. If you don't have a calculator out, you're the person I want to call on. You get that, right? I have to call on somebody. So it'd be in my nature to find the person who could have to say, I don't have my calculator out. So don't be that person. Tyler, what did you get for the tension? 3.1 newtons, and let's see, Dukan, what do we get for the weight?
I'm not certain if I use grams or kilograms.
We want to use kilograms, so it'd be 0.65 times 9.8.
6.37.
All right. So the first thing that I think most students think to do is that they could just plug it in to this equation and that would determine mu. And yeah, we'd get something here like what, 0.5, 0.4 something? And you'd walk away and say, that's it. That is not a very good lab. First, we're using a single data point to determine what mu is. Now, yes, we could repeat this with the same conditions and maybe get the same number over and over again. That would give us more validity. But the problem with that is it doesn't allow for a range of data. In trying to describe a lab, one of the things that you should always attempt to do is not rely on a single data point, but try and rely on a range of data points. In order to do that, you should really consider if you can find something that you can change in order to be able to make a good decision about what you could get for a range. What is something we could change about the experiment that would help us develop a range of values? Adam?
Mass,
When you say mass, what do you mean?
changing the weight of the car or of the block.
Sure, that would probably be the easiest way to do so. Just put something more on there. The first thing this does is it ensures that we didn't get a one-off measurement for some peculiarity in our system. But the second thing it does is it begins to develop a range of data points. Look, friction equals mu times the normal force. It screams a linear function. Double the normal force, I expect a doubling of the friction. So I added more weight. We expect to see the friction force go up, not mu. We think mu is the same all the time because mu is about the surface. If you only do one data point, you're not really showing that. So a range of data allows you to show not only what mu might be, but it also allows you to prove the relationship. We should get a lot of data points. We should see if they're linear. So the next thing that you should consider in experimental design, after you have figured out all the things you can measure, is how do you manipulate one of the variables in order to cause a change in the other? How are the variables related? Our plan shouldn't just be to take a single data set. Our plan should be to create a data chart, something that eventually will give us friction and normal force. We know we're doing that from the tension and the weight. And by looking at this, seems pretty clear to me that we should be trying to put the frictional force on the y-axis because it's in the numerator, and the normal force on the x-axis because it's in the denominator. Remember, linearization of data suggests that if we do that, this should produce a linear function whose slope is the coefficient of friction. That's how this should be done. It's so much better than just saying, I'm going to get one data set and divide the two numbers. Whenever you can, you should always try and produce a range of values. It reduces error and is the best way of demonstrating that. So we expect this to go up some. Let's see if it does. Redo the lab a bit. So I'm gonna walk on over here, push the car back to where it was. It is indeed heavier. So try not to step on any of my wires here. Ready, John? Here we go. What was our new number here?
5.5.
5.5. So I added 500 grams. So the total thing is 1150 or 1.15. And we had 5.5 newtons of tension. So our first data point was 3.1 and 6.4. And now our next data point. What's that, about 5.1? 5.2. 5.1? And what's our new normal force? Somebody at home, give this to me. 1.15 times 9.8. Don't make me call it a name. Come on, somebody volunteer. Okay, Keenan, could you do it, please?
11.3.
Thank you. See, that wasn't terrible. What's an appropriate number of data points? At least. You should try and always get 5 or more. Although 3 data points specifically says line, it's not enough to determine whether you have a linear function. 5 data points is better. So you should indicate as many as possible, but 5 or more. So this is a relatively straightforward coefficient of friction lab. It hits all of the points you want to do. It reduces error and attempts to use relatively straightforward equipment that you can find in any physics laboratory. One of the things I also want to promote here is you can replace a lot of the things you see here with simpler items. We don't have to use a force probe and interface. You can use a spring scale. That would do the same. In the old days, the way I used to do this lab is I'd put a pulley on the end because I didn't have spring scales, even though they're cheap. And instead, we would attempt to try and create the conditions for a constant velocity by hanging something off the end. So I'd get a mass hanger like this, hang it off the end, and we'd add weight to the end until the system just began to move at constant velocity. It would require that you tapped on the car to get it started because you had to break static friction. But it was a similar method. The problem with this method, and one reason I would not do it as a lab any longer, is you have to find the perfect amount of weight to put here for it to move. And that usually is very difficult. It's almost always going to accelerate and not just slide at constant velocity. So not a better lab, probably a worse way to do it. All right, now, the actual lab you guys were supposed to do, the one that's in the FRQ, is about measuring static friction. So static friction is a little trickier to measure because it's an inequality. Now, we did a static friction lab back first semester. And if you remember, it involved a book. Do you remember? We just put stuff on the book, measured the angle. I want to show you 2 different ways to do a static friction lab. The first way isn't going to be using the book. We're going to try something different. The first way uses the force probe again. The difference is that this new way is going to measure force as a function of time. And what we're going to do is we're going to slowly pull on the string until we break friction and the system starts to move at a constant velocity. If we measure force as a function of time, we should be able to see the ever increasing force until we reach a maximum where static friction is broken. And then it should drop down to kinetic friction. Now, I'll be honest, this is not a great way to measure this. It doesn't work great, but it is a way, and it's worth noting because they put it on the exam before. So let's take a look at doing it this way. To do this, I have to set up my probe to measure force as a function of time. And I've already done that. It's set to measure 2 seconds worth of data at 50 samples per second. So let's go ahead and give it a try. I need my force probe. I need my string. And I'm going to start the data collection and I only have 2 seconds, so I've got to be ready to go. Wasn't great, I'm gonna have to do it again. So we'll try it again. That's the problem with this lab. I want to start with 0, but only get 2 seconds. Okay, so do you see what I see there? You see how there's an increasing force in the beginning, it peaks, and then it immediately drops back down once the cart started moving. Now, what that is a way of getting the static frictional force. You have a graph that looks something like that. It's not great in the beginning, right? Something like this, and then it drops down like that. Now, we took 2 seconds of data. This portion of the graph from here to here represents the time in which static friction was operating. Now, it wasn't nice and linear because my hand was probably not nice and regular. But what you should be able to see there is that this range of forces from here to here was unsuccessful at breaking friction. I applied the force, but the car never moved. This is demonstrating the inequality. So if you want to demonstrate the fact that friction is an inequality, you would have to find a way to apply forces that were less than friction and show that as the frictional force increased, the cart, or the frictional, I'm sorry, as you pulled on the cart more, the frictional force was increasing until you reached a maximum. That is the point where it was equal. So this moment right here, that was the maximum static frictional force. Then it immediately dropped down. This is where kinetic friction took over and stayed relatively constant as I pulled on it because the frictional force is constant. Now, the problem with this is, although you can get a data point because we could find out what the size of this frictional force is and we could solve this knowing that it's an equal sign now because we reached the peak. And you could do that over and over and over again. But you saw the graph, the real graph that's produced is not so neat and clean. And it's not particularly tidy. And it's not particularly easy to get the data. There's another way to get this data, but it requires that you remember a little bit about doing a free body diagram and solving a force problem. So what I'd like you to do is you get to take the next few seconds and work this force problem out. I'd like you to tell me what mu equals. I'll let you use, say, the mass of the book and the angle and G. But see if you can work out what mu equals. If you remember doing this lab, you know that it works out to be something nice and easy. If you don't remember, well, free body diagram, coordinate system, component vectors, and apply Newton's laws. And don't be the person that when I call on says, I'm having a little trouble with that. If you're having trouble, figure it out now. So I'm going to pause the video for just a second. You only get a moment or two to do this. All right, so let's go ahead and move on from this. So we're going to start with the free body diagram. Kayla, tell me how I would draw all these forces real quick.
Okay, so the normal force isn't going to be straight up. It's going to be perpendicular to the inclined plane.
Perfect.
But gravity is going to be mg straight down. And then
Excellent.
friction should be going up the ramp.
Excellent. All right, free body diagram done. So let's see, Anthony, what's a good coordinate system to use here?
Well, I put the normal force as like the straight up as a y-axis and the friction as the x-axis, and then I took the components of the mg.
Excellent. So let me just kind of draw that in. Great. So negative y, negative x. So, and you had the components of mg. So what are those two components?
The vertical one is mg cosine theta, and the horizontal one is mg sine theta.
Excellent. Now, we want this to all be balanced, so it should have a look to it like it is balanced. So that checks off 1, 2, and 3. So let's see. I know, Samantha, can you apply Newton's laws for me?
I was kind of confused with it. I didn't get to the mg cosine theta or mg sin theta.
All right. Do we think this is a first law problem or a second law problem? No, we actually want it to be a first law again. We want the object to stay at rest we just want to figure out what, how to get mu from it being at rest. So we're going to still start with the idea being that the net force equals 0, and we're going to break that up into the x direction and into the y direction. Okay, so Tanner, what do I do with that?
So you're gonna do your x direction, which would be mg sine theta and f, where it's sliding down the ramp, so f would be negative.
Actually, not sliding. We want it to stay there.
Well, it's not sliding, so f would be negative,
Okay.
and then solve for 0, or like move f over.
I'm just going to cut to the chase. They're equal, right?
Yeah.
Yeah. We're going to try and speed this up some.
Okay, and then do you want me to do the other one?
Mhm.
Normal force equals mg cosine theta.
Excellent. Now, just because of static friction doesn't change the fact that it's not going to have a similar relationship. What we're trying to do is we're trying to push the envelope to get to the point where the friction is right at the edge. To do that, we're going to lift the track up. Remember, you guys lifted the book up. Want to find the angle at which it just barely started to move, and then back it off a little bit, because that has to be right at the threshold. When we do that, we get friction over the normal force, which is mg sine theta over mg cosine theta. Of course, that means that mu is just equal to tan theta. So in this version of the lab, we are only looking for an angle. Now, there's good and bad about this as a lab. The good is that we're just looking for an angle. It uses good solid theory to tell us that once we have the angle, we have the coefficient. The bad, changing the weight of the car really isn't going to provide us another data point. We can't get a range of data from this. We could have gotten a range of data with the other one with the graph and stuff. Can't get a range here. We get a single answer. Now, you have the coefficient of friction from our prior practice here. You at least have an estimate from over here. This is the coefficient of kinetic friction. We know that the static frictional force is going to be a little bit greater than this. This gives us a starting point though. Kind of tells us what angle to start at. Can you work this backwards real quick? If this is the coefficient, and we know our coefficient is a little more than this, what angle should we be starting at? All right, so Brandon, what angle are we starting at?
30.
All right, so the inverse tangent of 0.48 is 30. I have to be in degrees for this one. Otherwise, you're gonna give me a radian answer, but this is in degrees.
26.
All right, so we should be safe up to 26 degrees. All right, that's 20. 25. You know what's really kind of funny is that if you approached a road that was this steep, you would think that that's a pretty steep road, but it's only 20-something degrees. So when we think of road grades, you might not know this, but roads are graded as a percentage. So a 100% road would be a 90-degree road. So they do it by percentage. So, you would never have a 50% grade, right?
Good morning, Signals High School. It's time for morning announcements. Please stand for the Pledge of Allegiance.
Right there, right?
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God.
So you guys might not have seen that because we got broken in with the announcements, but take it right up to about 26 degrees. The idea is to get right to the point where it starts to move and then back it off. Oh, You're right about there. Going a little too fast. Don't want to shake it either. Shh, don't sneeze. Right there, it's 28 degrees. Not terrible. Not terrible at all. So as a method goes, it's okay, it doesn't work terrible, but like I said, it's a one-off. So once you get that, there's nothing else you can really do. You can put more weight on it to see if you get a repeatable answer. It doesn't really produce a range of data. Nothing you could graph where you found new. Make sense? All right, now we only got to really do one lab, a coefficient of friction lab. Tomorrow we're gonna do 2 different labs. Please do the coefficient of friction problem tonight. It should take you about 15 minutes. And that's what I'm asking. If you're looking for ways to improve your scores, you should probably try and do the other practice I posted. That would be the way to try and bring your grades up. So aside from that, are there any questions?